So welcome. Good morning, everyone. My name's Kent Hubble. I'm the current president of CAPE. And uh, CAPE, of course, you perhaps already know, is Cornell Academics and Professors Emeriti. And we look after a variety of events and services on behalf of emeritus faculty at Cornell. So I'd like to welcome our friends and colleagues here in the Kendall Auditorium, and well as those on Zoom. I'm hoping that there are many of them. We're introducing today's speaker. Before we introduce today's speaker, I want to extend CAPE's sincere appreciation to Kendall for making their venue available for CAPE Lecture Series. Their hospitality is not only including AV support, but also free parking, which of course is an important commodity in our neighborhood. And of course, the freshmen, which are always a pleasure to enjoy. I'd also like to thank Melissa Rockledge, CAPE's program coordinator, who will be providing support on Zoom. Those of you on Zoom are encouraged to submit questions during or just after the lecture in the Q&A box, which Melissa will be moderating. The speaker will take questions from both the in-person and Zoom audience at the end of the lecture. For those of you in the room, please make sure your cell phones are silenced on vibrate. And for those with hearing aids, this is good news. The auditorium has an induction loop. If your hearing aids have a telecoil setting, turn on the setting key, and then sound from the microphone will go directly to your hearing aids. So now turning to our speaker. Yes, you may have seen the September 10th New York Times article by David Overby. It was entitled, 10 years ago, astronomers made an epic discovery with the Laser Interferometer Gravitational Wave Observatory, otherwise known as LIGO. Cosmology hasn't been the same, and he says it might not stay that way much longer. I recommend the article for those of you who haven't seen it and are interested in the whole field, because it does a nice summary for those of us who are non-scientists. He also then remarks about how contingent the funding is at the moment by virtue of the administration's most recent funding changes to the research that so many wonderful scientists are undertaking around this field. Suffice it to say that since hearing the faint chirp of a collapsing BBH, that is a binary black hole, I've been fascinated by this new window on the universe that has opened up vistas not previously accessible using optical and radio telescopes operating in the electromagnetic spectrum. Now astronomers can observe the universe with gravity wave radiation of a variety of wavelengths. That's what we'll be hearing about today. Unless you have unique spidey senses, there's nothing to feel when a gravity wave passes the Earth. This so-called ringing of space-time is not the sort of thing that will rattle the dishes in your china cabinet. But there is something on your iPhone that called an app that will help you identify when a black hole crosses the Earth. And I'll let you hear the wonderful sound, one of many, that will come across your phone when a gravity wave passes the Earth. Listen to this. How about that? So for all of you black hole enthusiasts and gravity wave enthusiasts, you too can wake up in the middle of the night to that wonderful little sound. So on to our speaker. Jim Cordes is the George Felstein Professor of Astronomy here at Cornell. Oh, I'm sorry, never mind. Jim Cordes is the George Felstein Professor of Astronomy at Cornell. He came to Cornell in 1979 as an assistant professor, made use of the Arecibo Observatory for more than 40 years in studies of neutron stars and other objects. By the way, working along with Hal Craft. His PhD in applied physics is from USC San Diego, UC San Diego, and his Bachelor's of Science is in electrical engineering from UC Santa Barbara. Before Cornell, he was a postdoc at UMass Amherst with Joseph Taylor in the years immediately after the discovery of the binary pulsar that led to the 1993 Nobel Prize in Physics by Holtz and Taylor. He was a principal investigator of the US Technology Development Project for the Square Kilometer Array in the early 2000s. And he is a co-PI on the NSF-funded Physics Frontiers Center for NanoGrav, that is the North American Nanohertz Observatory for Gravitational Waves. His work concentrates on turbulence in the interstellar medium, neutron stars and black holes, and gravitational waves. He's worked extensively on fast radio bursts, FRBs, for those of you in the know, and an enigmatic phenomenon of cosmological origin. In recent years, data analysts in these areas has made increasingly use of machine learning and neural networks. And if any of you go to the research, you can see it in spades. It's all very, very neural network. Okay. To distract himself from the frustrations of his professional work, he enjoys street landscape photography and bird photography, and a little bit of astronomic photography as well. So with that, please welcome Jim Cordes, our speaker for the day.
Okay, so I guess I need to hold the mic close. Yes. Oh, okay. Well, thanks very much for the invitation to speak. You can see the title of my talk follows much of what Kent just said. I'll be talking about gravitational waves and black holes and some other things. So basically what I'll be talking about first is neutron stars, because the project that I'm involved with, the NanoGrav project that Kent mentioned, makes use of neutron stars as detectors of gravitational waves. So it's sort of a two degrees of separation, but two of them involve astronomical objects. So I'll talk about black holes, small ones and big ones, and I'll talk about the, I call it here the symphony of black holes. The fancy way of saying it is the stochastic background of gravitational waves produced by black hole binaries all over the universe. And then I'll say very quickly what the next steps are amid this extreme funding situation that we find ourselves in. So, so the basic picture that I will get to is this. This is showing a faraway galaxy with a supermassive black hole binary inside it. And then the grid pattern there that looks warped represents space-time. And so space-time is warped by the gravitational waves produced by that black hole binary. Those waves come from far away and reach the Milky Way and affect the pulsars, which are shown here. You can see the stellar-like objects with the lines through them. Those are pulsars that we monitor with radio telescopes. And so so all of the things I'll talk about will lead up to, like, okay, how does this work? So one of the main telescopes we have used in NanoGrav is the Arecibo telescope. The group of people that you see there that's from a NanoGrav meeting we had at Arecibo, I think about 15 years ago. And so you can see maybe 50 or 60 people. That has grown now to almost 400 people across North America. So the NA in NanoGrav means North American. Okay, so we have the NanoGrav logo there. The Arecibo telescope unfortunately collapsed in 2020. We are making do with other telescopes for now, but what I will finish with is a description of the new telescope that is going to be built over the next few years. It will be actually far better for us than Arecibo. I can say that, how did I get here? So just on a personal basis, I probably made 150 trips to Puerto Rico in my usage of Arecibo over the years. And so how did I make it to Cornell. Well, to make a long story very short, if I had not worked in a gas station in 1970, I probably wouldn't be talking here right now. So I can, if you're interested, I can talk about that offline. So what is a pulsar? Well, here's an animation showing a beam of radiation, radio waves whipping around due to the rotation of the neutron star. On the left is a cartoon of what a pulsar looks like. It's a very tiny neutron star, that circle in the center. There's a magnetic field that is embedded in that star. And the radio waves come about from relativistic particles streaming along the magnetic poles. And the magnetic axis is skewed from the spin axis. And that's why we see this, these rotating beams. And when the beam points at us, we see a pulse. These objects are produced by heavy stars, the most fairly massive stars that explode as supernovae and leave behind a core, and that core is a neutron star. So just, what you can measure is something like this. This is a set of pulses jumping around, you can see. So basically, there's a lot of activity in the magnetosphere of the pulsar. And so the magnetic field guides the particles that radiate. So it's sort of like a flashlight, but the flashlight is not that stable, okay? But by virtue of the rotation, which is very stable, when you average many of these pulses together, you get a stable shape that's unique to each pulsar. And we exploit that fact in our gravitational wave detection. So now I was debating whether to play the sound or not, but given all the effort work, this is what the of course the pulsars don't do it. That doesn't prevent us from this is from a pulsar that's rotating. Neutron star is an object that has mass, more mass than what is in the sun, but the object is about the size of Ithaca, and it's spinning very rapidly. Okay, so back to the cartoon, I just wanted to explain a few things here. So we have the rapid rotation. The fastest rotating neutron star is 600 times per second. My colleague Tommy Gold liked to say that that's faster than your kitchen blender rotating on high. These are strongly magnetized, so 10 to the 12 Gauss or 10 to the 8 Tesla, if you like Tesla or Teslas. That's about 1 trillion times the magnetic field strength of the Earth. And that makes these objects very weird. They exert strong gravity, but they also exert strong electric fields. So anyway, if you take a teaspoonful of neutron star matter, it would weigh about 100 million tons on Earth. So basically what you can think of a neutron star as a giant nucleus, where all the space between, say, the electrons and the protons in an atom, that space has been squeezed out, and the electrons and the protons are now neutrons. That's a simple way of saying it. So when you spin a 1 trillion Gauss magnetic field at these rates, you generate big voltages. So it's 1 trillion volts that is across the magnetosphere here. And that's what accelerates the particles. And that's why we see these things. The neutron star is interesting in itself, and it may seem implausible that we can say anything about what's inside a neutron star, but there are measurements that tell us, some aspects of what's in there. So the neutron star has a solid crust, mostly made of iron, and then inside it's mostly neutrons that are in a liquid form. So we see manifestations of that. So the history of this is interesting. The neutron itself was discovered in 1932, but it took until 1967 when Jocelyn Bell discovered the first pulsar. In between, so it only took a year for two gentlemen, Botta and Zwicky, to say, well, we've got neutrons, so there must be neutron stars. So that just was a year after 1932. And then Oppenheimer and Volkoff in 1939 developed models for neutron stars. And then there was sort of a dark ages of No, people thought you'd never be able to detect neutron stars, but they were discovered in 1967. So just to put that in perspective, there's a hierarchy of stellar masses, right? The sun is sort of a Goldilocks in mid-range mass. It will produce a white dwarf when it has exhausted its fuel, its hydrogen. Medium mass stars form neutron stars. The most massive stars turn into black holes. So that's the landscape. So what good are these, besides gravitational wave detection, which suffices as far as I'm concerned. But if you go back to the early 70s, the Pioneer 10 and 11 spacecraft had these gold plaques attached to them. And those two spacecraft have left the solar system. These plaques show obviously what people look like. It shows what the spacecraft looks like. At the top left is a depiction of a hydrogen atom. And the bottom row there shows the solar system and the trajectory of the spacecraft. And then this spoke-like diagram represents the directions and distances to the few pulsars that were known at that time. And then what's more interesting is you can't see it. I can barely see it here, but encoded along each line in digital form is the spin period of each of these pulsars at the time that, as of 1972, but because of the magnetic field attached to the neutron star slows down in its spin. So imagine an alien civilization, stumbling across this spacecraft 1 million years from now. They would be able to tell where it was launched from and when it was launched, because the pulsars will have spun down and they can work backwards as well as we can. So this was Carl Sagan and Frank Drake are the ones that made this happen. And similarly for the Voyager spacecraft, the Voyager records, the gold records, there have other information and sound and images, but also the spoke-like diagram that you can see there on the record with the same premise. Well, pulsars are clearly high energy objects, so why not sell energy products with the pulsar name? You can find all kinds of things with the pulsar name. You can also sell t-shirts and record albums. So the Joy Division punk rock group made use of this set of pulses right out of Hal Craft's 1970 PhD thesis from Cornell. And then, then a little bit more quantitative and scientific in nature, people have looked at making use of pulsars for cryptography. So basically the random aspects of pulses can be used to generate random numbers. So this was a recent, the physical publicly verifiable randomness from pulsars. That's a fairly recent paper from about 2 years ago. But in my first year at Cornell in 1979, I did consulting for a Defense Department think tank in the context of, at that time, the MX missile system was being proposed and partially developed. And then in conjunction or in parallel, the SALT II, the Strategic Arms Limitation Treaty agreement, was being hammered out. And the essence of that was that we needed to be able to verify how many missiles the Soviets had and vice versa. So what better way of choosing the random missile silos than using pulsars to choose the silos? Needless to say, none of this ever happened. The MX missile system wasn't built. The SALT II agreement didn't happen, but I did get paid. Okay, so then a little bit closer to home, about 20 plus years ago, a set of my friends and I wrote this paper about using pulsars as tools for fundamental physics and astrophysics. This was not a new concept by any means. We didn't invent that notion, but we sort of spelled out in some detail how that could work. And then in 2023, the NanoGrav project used a 15-year data set to basically detect what we call the stochastic background, the symphony of gravitational waves coming from black holes. So I need to explain a lot now. So let's look a little bit at black holes. So the notion of black holes actually is quite old. It goes back to the late 18th century. So John Mitchell and Laplace applied Newtonian physics to the idea of can light escape an object once it's above a certain mass? Einstein and Schwarzschild did a better job. Einstein had a much better theory of gravity and really sharpened the concept. Schwarzschild sharpened the concept of black holes. Then as time went on, Oppenheimer again was in the business. Models of black holes. They weren't called black holes because that term wasn't invented until 1968 when Wheeler coined the term. Roy Kerr solved Einstein's equations for spinning black holes. That was a challenging thing. And then 1963 was also a landmark year in a number of ways, but the discovery of quasars. Quasars we call today active galactic nuclei, and I'll say more about that. So really the first identified stellar mass black hole was in 1971. So there's an object in the constellation Cygnus called Cygnus X1. The X means it's an X-ray source. What was seen was an X-ray source that had a companion. And so by monitoring the system, astronomers were able to establish that the dark object had a mass of 20 solar masses. That's far too big to be a neutron star. It had to be a black hole. Then it's going back to the 60s. In 1964, Ed Salpeter and Zeldovich proposed that active galactic nuclei, quasars, are actually very massive black holes that somehow emit radiation that was detected. So the present picture is that it looks like every galaxy that's out there, and there are a lot of them, every one of them has a central black hole. And that's what is of interest to us. So, so let's look at the center of our galaxy. So here's a very beautiful image of, it's about 10 degrees across. This is a radio image of the galactic center obtained at 1.5 gigahertz with the Meerkat Array radio telescope in South Africa. I think we all know what a gigahertz is, right? Our Wi-Fi is 2 gigahertz. FM radio is at about 100 megahertz. So that may seem like a silly statement to make, but when I ask the question of students in one of the lab courses I teach, like, what's the frequency of FM radio? They have no idea, which is, everybody streams, right? Anyway, this is a beautiful picture. The yellow patch right in the center there is an object called Sagittarius A. That's a region with a lot of gas and stuff. You can also see round objects that are supernova remnants, these weird filaments that are tracing out the magnetic field in the Milky Way. So where the Milky Way's black hole is right in the center of that, the yellow patch. Okay, what happened here? There we go. The yellow patch, and it's far too small to see. That yellow patch is much bigger than the event horizon of the 4 million solar mass black hole that's there. That's called Sagittarius A star, where the star refers to the fact that there's a very compact object in the center there. It was discovered in the early 70s with a radio telescope, and then it took a while to figure out what it was. So how do we see black holes? Well, the cartoon there on the left shows the black hole in the center, and then there's a disk, similar to the rings of Saturn in some sense. And that accretion disk, as it's called, is fed by stars that happen to make their way towards the center of a galaxy, and they get accreted into that disk, and then that material in that disk spirals into the black hole. The black hole gets more massive, and the way angular momentum is gotten rid of is by emitting these jets that you see in blue. So that's the picture that actually holds for low mass black holes and the most massive black holes. The other frames in this slide show the jets that you can see with radio telescope images. So on the top right there, you see these very beautiful jets coming out, and then as they encounter surrounding gas, they sort of waver around. And you can zoom in, and what I should say is that the optical galaxy, so in the far right there at the top, I guess I can use my cursor here if I can find it. Anyway, if you zoom in, if you look at the galaxy that has this black hole, it would be actually quite small in that right-hand diagram. Another version of this is on the bottom right, and then on the bottom left is actually a binary, a double black hole system. So you can see two pairs of jets, and there are two nuclei. So what happens is that these things will some of the, like that case and others, those black holes will eventually spiral around each other and merge. So let's go back to the galactic center then. So keep this picture of the accretion disk in mind. So a simulation of what the accretion disk would look like around Sagittarius A star is shown here, and it doesn't look like that cartoon at all, right? The reason for that is the black hole bends the light rays by what we call gravitational lensing and distorts things. And then the fact that you see, the image is dynamic is because the accretion disk has structure in it. And so the light from that different structure is bent in different ways and so forth. Okay, so in principle, you can image objects like Sagittarius A star and others, but you need a very big telescope, basically a telescope the size of the Earth. That's what, excuse me, that's what the Event Horizon Telescope is. That's a very long baseline interferometric array using antennas pretty much spread over all of the Earth. And you need that big set of baselines in order to resolve the very tiny accretion disks around these black holes. So there are two, so the EHT project has imaged Sagittarius A star there on the left, 4 million solar masses. And then there's a much bigger black hole in Virgo A, that's Messier 87, 9 billion solar masses. So these things are monsters. Let's look at a couple more images. If you zoom in on M87, or zoom out rather, this is what you see. So you see one jet, and then it smacks into the intergalactic medium. You also see on the left there, you see the smacking into the medium, but you don't see the jet. The reason for that is because the particles in the jet are moving relativistically. And so the left-hand jet is moving away from us, and so you don't see it. It's just too dim. The one on the right is coming more towards us, so it's enhanced by relativistic beaming. And then the last example I'll show is this one, Hercules A. Here you see both sides, both jets, and it's just very beautiful. You can also see in the right-hand one that there's structure within that lobe, a set of lobes. That's because the accretion is episodic. So you have these bursts of activity coming from the accretion disk around the black hole, and they are manifested way out. And again, the optical galaxy you can see there is the size of our galaxy roughly. These jets are going way beyond the optical galaxy. Okay, the last thing I'll say about these is these are all over the sky. These are not rare. There are millions of them known. Let's move on to gravitational waves then. So here we have another animation showing the stirring of space-time. I call it a cosmic egg beater there, but basically you have a binary system that's emitting gravitational waves. They propagate out at the speed of light. So that's what LIGO measures. That's what we measure with pulsars. So how does that work? And what does it mean to have ripples in space-time anyway? It's actually, I think it's kind of simple. This is the way I would explain it, is that gravitational waves move the goalposts. Gravitational wave can stretch space or it can squeeze space. That means light either has further to travel or a less distance to travel. So the analog here is with a kicker. Suppose a really big gravitational wave came through the solar system and moved the goalposts. That kicker might be disappointed because he misses the goalpost. Or maybe the gravitational wave moves the goalpost inward, and then the ball hits the post or something. So the way we quantify this is with something called the dimensionless strain. So on the bottom right there, it says a gravitational wave of strength h changes the distance L by an amount delta L. Delta L over L is quantity little h. And is that quantity little h relevant to the things that, that we're talking about here are absurdly small, depressingly small. Like in the case of LIGO detections, it's 10 to the minus 23 or so. So you're talking about a very tiny change in distance. For the pulsar project, it's much bigger. It's 10 to the minus 15. But anyway, so people thought LIGO would never detect anything because it was just so challenging, very difficult. And same thing with the pulsar detection that I'll be talking about. So let's look at some of the LIGO detections. So LIGO consists of 2 sites, one in Washington, one in Louisiana. Each one has 2 arms perpendicular to each other, and laser beams propagate back and forth and are reflected by mirrors on pendula at the ends of the arms. And so if a gravitational wave comes through, you can measure the distance that's changing as the pendulum swing. That's sort of the simplistic description of it. But the thing is, things like rolling, tumbleweeds rolling down the road are also detectable with this. So you have to be able to tell the difference. And that's why there are 2 sites. And so what the article Kent was referring to is putting that system in jeopardy. And it's been it's produced a fantastic set of discoveries. So on the right there, I'm showing the first detection of gravitational waves 10 years ago, almost exactly. An event was seen at both sites, and what you can see there is it's sort of noisy, but it's a growing signal, and it gets larger and larger, and it oscillates faster and faster, and then boom, that's when the 2 black holes have merged. So when the black holes merge, you can work backwards from the data and estimate that the 2 black holes were each about 30 solar masses. And so that means you would expect a 60 solar mass black hole with the merger, right? Well, not quite right, because about 3 solar masses of energy was lost to gravitational waves. So it's a very peculiar thing here. So since 2015, LIGO has detected a large number of these black hole events. And so now people are in the process of studying the mass distribution of these black holes. And that gets you into the terrain of like, okay, how do these form? What determines their masses and so forth. Then a couple years later, in 2017, a neutron-star merger was detected. And I call this, and other people call this a Rosetta Stone. So it's known in the field as GW 170817. That's sort of a magic phrase now that anybody in the business would understand. So what's interesting about this system, you see on the top 2 of those 3 blue frames is the chirp signal, that like what you heard. But the interesting thing about this one was that it was localized on the sky. It was detecting gravitational waves first, localized on the sky, and then it was studied all across the entire electromagnetic spectrum, from radio waves to the optical to X-rays, gamma rays. And so it was established then that there was, the elements that were produced in this merger conform to the ideas that have been around for a long time. And so basically we understand element formation even better than before. And so at the bottom there, it says 10 Earth masses worth of gold and platinum were produced in this merger. So I think given the current price of gold, this event is much more valuable than it was in 2017. Anyways, because of that multi-messenger aspect, gravitational waves, electromagnetic waves, that we call this a Rosetta Stone. So it was called, so it produced something called a kilonova, the breakthrough of the year by Nature magazine. And if you look at the periodic table, it was known for a long time where most of the elements came from, but not necessarily in detail. So there are elements, the ones that I've circled there, iridium, platinum, and gold. are among those in purple that are produced, they're all produced in neutron stars. So my gold ring and any gold you have most likely came from a neutron star merger. Okay, so let's move on. So let's talk about the spectrum of gravitational waves. So this is a schematic showing the dimensionless strain on the vertical axis, and then frequency, gravitational wave frequency along the bottom there. And there's a huge range. This is going over 16 orders of magnitude in frequency. That's similar to the span going from radio waves to gamma rays in electromagnetic astronomy. So the point is, if you want to have a comprehensive view of everything in the universe, you need to cover this whole range. And that requires different technologies. So you can see the patch on the right there is labeled with LIGO. That's sensitive to kilohertz type frequencies, same frequencies as what we can hear. Then there's a space project called LISA that will work in much the same way as LIGO, that'll be sensitive to millihertz frequencies. And then the nanograv pulsar approach is sensitive to nanohertz type frequencies. So you may not be well calibrated in nanohertz, but another way of saying it is that the wavelength is a light year or so. So back to this diagram then. So the nanograv project, again, monitors the pulsars to detect gravitational waves coming from the far off universe. So how do we get, I showed you pictures of, mostly isolated black holes, with the jets. But so where do the binaries come from? Well, they come about from mergers of entire galaxies. So what you can see here is a merger of two particular galaxies. This is not a cartoon, this is the real thing. And we see mergers happening in different stages all over the universe. So eventually the black holes will, these two galaxies will merge and the stars will collect together in a bigger galaxy, and the two black holes will find themselves in a binary, and eventually they will merge. There are a few minor miracles that have to happen in those stages, but it does appear to happen. And so our detection of the gravitational waves with pulsars actually demonstrated that those mergers actually happen. So here's a cartoon showing, I hope, yeah, here we go. Just along the top there, it's showing a galaxy merger. The stars coalesce. It says stellar core merger, so the most massive stars settle into the center of the new galaxy. And then in the core of the galaxy, you've got the two black holes orbiting each other. And if they do merge, they will produce oscillatory gravitational waves. And then when they merge, they emit a final gasp of gravitational waves and then settle down. So up until our detection, it wasn't known if the mergers actually happen, because in order to spiral in initially, the black holes have to, there's a process called dynamical friction where all the other stars in the center of the galaxy, in a sense, force the two black holes to merge. And it was not really known if that process really worked. People had worked it out, but it required certain conditions. Evidently, it does work. Okay, so pulsars as gravitational wave detectors. Think of it as this: the entire universe is filled with gravitational waves. They're coming through this room right now. I don't feel a thing. So we have a pulsar there and then the Earth. Both are being bathed in the gravitational wave background. So as the pulses propagate from the pulsar to Earth, they're affected by that background as well. And so we can measure whether a pulse is arriving early or late. Have the goalposts move for those pulses. So here we have, just to put it in context, this is an artist's rendition of the Milky Way, what it looks like. It's a spiral galaxy with a bar, that yellow elongated thing. And then I've indicated where the sun is. And the red square represents the volume where we have of the pulsars that we're monitoring. And then on the top left there is showing another spoke diagram of these nearby pulsars. The green things represent structure in the local interstellar medium. So anyway, we're monitoring those pulsars, almost 70 of them. And the gravitational waves we can detect, or at least establish that we can detect, are detecting them, are the waves passing through the solar system, not the ones passing by each pulsar. So what happens then is this. I'm showing the two modes of gravitational waves. They're called the plus mode and the X mode. And think of a gravitational wave, excuse me, as something that stretches or squeezes space-time. So when the pulse encounters the gravitational wave, it's either going to arrive a little bit earlier or later. And the amplitude of the effect that we did measure was something like 100 nanoseconds over a 15-year period. That sounds like Mission Impossible, or it did sound like Mission Impossible, but it was pulled off. So basically, pulses arrive earlier for half of a gravitational wave cycle and later for the other half. So how well can we measure these things? Well, here's a depiction of the Crab Nebula, which has a nice pulsar in its center. We saw the nebula explode. Humans saw the thing explode in 1054 AD. So this pulsar emits radio pulses. They take about 6,000 years to get to us, and they're less than a millisecond wide. And then we can establish how when that pulse arrived at an observatory to typically better than a microsecond. And that's what you have to do in order to dream of measuring gravitational waves. So let me give another example of the sensitivity of the measurements we make. So take a drop of water, which is about 0.05 grams. That's about 10 to the 21 molecules. And then spread it into a cylinder that's 5,000 light years long and 1 square centimeter in cross section. We can easily, and if you dissociate the water and ionize the hydrogen and the oxygen, we can easily measure that. And the way we measure it is by this so-called dispersion effect that you see in the blue box there. We have frequency along the y-axis, time along x-axis. That's about 1 second of time, 100 megahertz bandwidth, centered on something like 1 gigahertz. The slantedness of that line you see represents the pulses arriving early at the high frequencies and later at the low frequencies. And that's entirely due to the ionized gas along the line of sight. So not only can we measure a drop, we could measure a drop of water spread out in this way, but if you chop that drop into a million pieces, we could detect an individual piece, individual droplet. Okay, so then it's still not that easy because we make these measurements on a moving platform, the Earth. The Earth is moving around the sun, it's spinning, it precesses. We have continental drift, all these nasty things that kind of mess up what would be a simpler picture. So what we do is we refer the arrival times as we measure them on Earth to the solar system center of mass, the barycenter. So that sounds simple. We just need to know where the barycenter is or where the Earth is relative to the barycenter. Well, that's not that simple for the precision that we need. So thankfully, we have people at the Jet Propulsion Lab and other places that have models for the solar system that give us the precision needed so that we can refer arrival times to the barycenter. And so JPL has these ephemerides, models of the solar system that we make good use of for this. And every time there's a flyby of a spacecraft past Jupiter and Saturn, those ephemerides improve. And that was actually required before we could make a detection. So let's see, how am I doing on time? Okay, more or less. Okay, so I think I'm fairly close here. So in 2 years ago plus, Nanograv made an announcement of the detection of the ensemble effect of the stochastic background. So we had 5 papers that in total were a few hundred pages. We also had a press event at the National Science Foundation. And so the lead one was evidence for a gravitational wave background. And then we had supporting documents, supporting papers like, okay, how did this work? What did the measurements look like? What are the constraints on supermassive black hole binaries. And then other people in the collaboration looked at things like, well, is there new physics in what we measured? What would the new physics be? Well, it might be a departure from Einstein's general relativity, for example. So as it says there at the top, our announcement was coordinated with other groups around the world. So there's a similar pulsar group in Australia, China, Europe, and India. And so it was all coordinated. And here's a sort of a picture of the different telescopes used by the different pulsar timing array groups, as we call them. And so we compete against each other on some days, and we collaborate on other days. So when we collaborate, we call it the International Pulsar Timing Array. And so it's, we sometimes use the word coopetition to describe the situation. And so it kind of works, but there's also this edginess. So where do we want to go with this? And I should say that I haven't really shown you any data because it's not as pretty as the LIGO data, but I'm happy to show anybody, some examples offline. So where do we want to go with this? Well, it's in the context of the universe itself. So here's a well-known graphic that's often used in talks showing the Big Bang on the left, a period of inflation. The cosmic microwave background was the photons that were flying around that became released from matter when the universe was about 400,000 years old. And then there was the dark ages, as it says there, and the first stars came into being about 300 million years after the Big Bang. And then everything has been evolving ever since, including black holes. So we think the way it works is that black holes grow in mass through mergers and acquisition. So we've got gold, we've got mergers and acquisition. So anyway, galaxies were quite different in the early days. And then through the process of merger, the galaxies evolve, they look different, and the black holes get bigger and badder. So that's the situation that we have, and we want to detect individual black hole binaries using the pulsar method. And we want to establish, what is in more detail, we want to establish what this process of growth of black holes is. So how can we do that? Well, this is my last slide, I think. It's this next generation telescope that we want to make use of. And so this has been in the works for about 10 years. It's led by Caltech. It's called the Deep Synoptic Array. The 2000 means that there will be 2,000 of these antennas in the Nevada desert, spread over about a 20-kilometer distance or range. And each of these antennas is about 5 meters in size. So this collectively, this will have much more sensitivity than Arecibo did. It'll have other capabilities that are better than Arecibo. And we think this is actually going to happen. The ground has not been broken yet, but it's expected to early next year. And one reason that everybody is optimistic is because it's not federally funded. It's privately, well, so far the antenna development is funded by Schmidt Sciences. So I want to thank everybody for their Google clicks and the advertising dollars that went to Eric Schmidt. So that's what that's really going to enable us to improve our sensitivity to gravitational waves and other neutron star science. We expect in nanograv to use about a quarter of the time on this instrument. It'll do lots of other fantastic things, but having a quarter of the time is actually a big deal for us. So I'll end with that and keep on clicking.
We have some time for some questions now. We have 2 questions on Zoom, and then I'll go to the audience. First one is, how much has the loss of Arecibo affected your research of pulsars?
It hasn't been catastrophic, but it's been significant. So about half of our data with nanograv came from Arecibo. The other half came from the Green Bank Telescope in West Virginia. So when we lost Arecibo, we had to, Arecibo was more sensitive than the Green Bank telescope. So that, that was clearly our preferred telescope. So we had to move some of the pulsars we were observing with Arecibo to the GBT. And we're making do, in this interim period. And so this is why DSA 2000 is so crucial for us.
Thank you. Next question. How does one determine the direction of the merger causing the gravitational wave? The distance between LIGO sites is not very large for interferometry.
For
Excuse my
interferometry.
Excuse my
Yeah,
pronunciation.
I think it's about 3 kilometers. The separation, from you've got the two arms. Those are a few kilometers long. And then just by comparison with, typical pulsar is 1,000 light years away.
Next question from the audience.
Hi, thanks for a great talk. This is a big picture question.
Okay.
So we thought we knew how the universe worked before we discovered black holes. Did that fundamentally change our notion of how the universe works? Or are we just now working out the details from those rules?
It's kind of both. I mean, we didn't know that the universe was expanding until the 20s. Oh, that was my timer. We didn't know that the universe was expanding until the 1920s when Hubble measured what looked like an expansion, and Einstein had to retract his picture of a static universe. But the notion of black holes had been around, in a coarse way since the 1700s. So I would say that the existence of black holes is a natural aspect of cosmology and general theory of relativity, as is the understanding of the Big Bang and how it's, how the universe is expanded. And now we know that it's accelerating in its expansion. But I think all those things are not in conflict. I don't think ever were, really. Does that? Yeah. Okay.
Okay, I'd like to ask a question with regard to timing, which you may have had on one of your slides, but if so, I missed
I
it.
skipped over a lot of things.
You start off with 2 black holes that are rotating round to another, and then they merge. Can you put that on a time scale?
Yeah, I skipped over some aspects of one of the slides. So the gravitational waves we measure with pulsars are just in the oscillatory part, as the black holes are just gently orbiting each other. Sorry, as the black holes are gently orbiting each other. That's about 1 million years before the actual merger. In the case of LIGO, I didn't really point it out, but the plot of the growing signal that I had, that was less than 1 second, going from the sort of oscillatory and then the big changes. So the amount of time it takes depends on the masses of the two objects. So a 1 billion solar mass object is going to have a much different timeline than a 30 solar mass object. We're binary.
Any more questions?
So what did you learn when you worked at the gas station?
Well, okay. This was in Santa Barbara, and in 1970, there were not many jobs to be had, and I needed to make some money. So it turned out that there was a gentleman from San Francisco that was opening up a new gas station, and he wanted to hire college students. So, I was getting desperate, so I applied, and lo and behold, there was one of my classmates, also in engineering, that got under the same scenario. We got to talking. We had both read about radio astronomy, and sort of a geek thing. But we said, well, let's try to do an independent studies project. So then, when the next quarter started, we were on the quarter system. So when that started, we approached a professor in electrical engineering, and he said, well, we don't do any of that here at Santa Barbara, but we know people at San Diego, UC San Diego, that do. And so we did that project, and I ended up getting my PhD at UCSD. We used Arecibo when I was in graduate school. And I got a postdoc with Joe Taylor in Massachusetts, continued to use Arecibo. So that's the path. So if I hadn't gotten that job, who knows? Maybe I would have been in Silicon Valley.
Any more questions?
Thinking about the current political climate in the United States, which is a hazardous occupation, but I'm curious if you were to give a presentation like this and you were appealing for government funding to continue this sort of thing, what sorts of legitimation would you have and what kind of questions would you get? In other words, would the people evaluating the spending probabilities within NSF or something like that, would they believe that this is all possible or that there never was a Big Bang or what was before the Big Bang? I'm serious. I mean,
No,
where would you be?
I'm seriously laughing.
Right. In some kind of epistemological or cosmological sense, where would you fit into the current American understanding of what we should be spending our money on and what we should be thinking about and worrying about?
Yeah, very good question. I think there's some people that just aren't convincible. But fortunately, there are still people in the government and at the National Science Foundation and NASA that understand the value of not just applied science and engineering, but also basic science. So it's nonetheless, it seems precarious for sure. I think we have to appeal to the public, that this is interesting. Astronomy may seem dispensable, when push comes to shove. But, there are lots of things that have come out of astronomy. For example, Wi-Fi, one of the inventors of Wi-Fi was an engineer in Australia working at their Radio Astronomy Institute. So there are a number of things like that. I think, maybe not so much with gravitational waves, but like with asteroids and comets, the threat of an impact on Earth, even Congress takes that seriously. Of course, that was 20 years ago. I'm not sure about the current. But they mandated that NASA catalog every asteroid bigger than 140 meters. So, that's sort of an extreme aspect of it, but it does connect to, like, why should you build a big, expensive telescope like Rubin to monitor the sky over and over and over again? Well, you want to find those kinds of impactors for one thing, but you'll discover all kinds of other things like supernovae and other things. So it's one package that you can't really divide up. So, we need to continue making that case. That's, I guess, a short answer.
One more question?
So, Jim, I know that Arecibo for many years was used to track near Earth objects that were floating by, and we've lost that capability now. Are there other radio telescopes that are able to do what Arecibo used to do?
Yeah, NASA with the Deep Space Network in California, there's a transmitter used for radar along with the Deep Space Network. And so they can monitor asteroids, but not as well as Arecibo. So there is a plan to use the Green Bank telescope in West Virginia to put a transmitter there and use the GBT as the receiver. But I think, it is basically a lost capability that, who knows, a sizable impact might not be for 100 years, maybe 1,000 years, could be next year. So, I'd rather know than not know.
I think we had one last question over here.
Great talk. Thanks very much.
Thanks.
What's the role of artificial intelligence in
Ah.
answering some of these big questions? And does it eliminate the need to even do this at all?
Well, okay. On a more mundane level, we use AI for some of our data analysis. So, for example, finding very weak signals in noisy data is something that we use convolutional networks for. But that's sort of a utilitarian thing. You're asking a much bigger question, like, can we ask ChatGPT, like, why is the universe accelerating? I don't think it would only give an answer that people come up with already. So I think in terms of the truly big questions, no, but I think in terms of aggregating pieces of knowledge from many different disciplines and putting it together, I think AI will be hugely beneficial. So I don't know if that answers it, but there's no real free lunch, I don't think. We have to keep working.
Jim, I want to thank on behalf of CAPE and the audience, thank you for a truly mind-expanding lecture. And I want to. And I want to.
Thank you, Ron.
And I want to bring your attention to the next lecture, which will be November 20th, and that'll be by Cornell's Mary Beth Norton. So now we will return back to Earth and look at it on a human scale. Mary Beth's lecture is going to be called, quote, "I humbly beg your speedy answer," end quote. Letters on love and marriage from the world's first personal advice column. Now, so that should be interesting. Mary Beth has just written a book on this subject, and that'll be the discussion. So see you back here in a month, and thank you again, Jim.
You're welcome. Thank you. Thanks, everybody.